Hello, everybody. So I'm going to be talking about conservation, so a little bit of a left turn from the finance talk that we've been having so far. And I'm going no notes because we're doing a duplicated display, so we'll see how this goes. So this is using AI to understand what works in conservation. And so what I'm going to talk to you today about is I'm going to give you an introduction to the Conservation Evidence Project, which is the group that I'm based in here in Cambridge. And I'm going to give you an overview of our AI evidence synthesis pipeline that we've been developing in the group, and then kind of performance evaluation of how well this pipeline has been working for us. So first of all, what is conservation evidence? So there's an evidence crisis in conservation. If you work in medicine or you work in aviation, evidence is at the center of everything that you do. So your doctor would be a very bad doctor if they weren't relying on the most up-to-date medical evidence that's out there. They take the clinical trials that happen, they take the case reports, and all the information from that feeds back into how we practice medicine. The same with aviation. If a plane crashes, we want to recover that black box, work out why that plane crashed, and stop that happening again in the future. But that isn't something that happens in conservation currently, where people are doing all kinds of things all around the planet. They work or they don't work, and it never gets kind of reported back in an efficient way to how we do conservation in the future. So this is the kind of goal of the Conservation Evidence Project, and this is the homepage of our website, and we do exactly what it says on the tin here. So we summarize the documented evidence of the effectiveness of conservation actions. And a conservation action is anything you could do to try and conserve a species or a habitat. And we've done this for, we've written 26 of these things that we call synopses. And so they cover things like forest conservation, everything you could do to conserve a forest, or birds, amphibians, coral reefs, marine fish, eels. We've covered all of these. And if you go to our website, you can see all these different actions. We have about 9,000 of these actions, things like plant wildflower strips or restore semi-natural grassland. And what we do is we find all the studies that have tested how effective these things are and then collated them in one place and summarize the findings from those studies into kind of 200-word paragraphs. And so anyone, if you want to do, anyone that's doing any kind of conservation could go to our website and find out whether there's evidence to support or refute the things that they're planning to do. And as a summary of the project so far, it's been running for about 20 years now. So it started in 2004, and we have read 700 journals, we've read over 1.2 million papers, and we've summarized those findings across 9,000 different conservation actions. And we've done all of this manually, by hand. People are reading these papers, they're summarizing them, and it takes a really, really long time. And it also costs a lot of money. And so we reckon we've spent about 75 years of researcher time producing the Conservation Evidence Database, which we offer for free. And so what I've been doing over the last couple of years, so I should also preface to say I'm a biologist, I'm not a computer scientist. But what I've been doing over the last couple of years is looking at how we can use large language models to accelerate the work that we are doing. And so this is kind of a very rough overview of what we're looking to achieve here. So we want something that will go out there and find all the academic literature. We want something that will then classify all that literature into whether it's for birds or for terrestrial mammals or forests. And then we want to summarize all of that evidence. And then that will populate our living evidence database, which is constantly having the stream of information fed into it, and so that people can access this database through what we're calling the Conservation Copilot to use kind of natural language interface to be able to remove that evidence, and so they can study it. So the first thing is finding the evidence. So we're very lucky here in that we've managed to, through the university library, reach agreements with a lot of the really big scientific publishers. And what we're allowed to do is we're allowed to bulk download all of their papers, whether they're open access or whether they're closed access. And we've downloaded about 15 million papers so far, and we're still going. And they weren't very happy about this, but they've had to let us do it. And they're not set up in any way to allow this to happen currently. And their back end is like a complete mess, and downloading these studies is harder than it should be. And we've also looked at grey literature. So grey literature is stuff that isn't academically published. These are government reports, reports from NGOs, from businesses. And we want to get information from those too, because there's useful information in there. And so what we did last summer with a couple of undergraduates here is we downloaded some versions of the Common Crawl. I don't know if people know what the Common Crawl is, but the Common Crawl is essentially before 2008, there were loads of robots going around the internet, scraping it and archiving it somewhere, and it got a bit of a mess, and people were quite annoyed about these robots. So they decided that why don't we just have one that does this, and then we all save it, and then everybody can access it. So what these are is archived versions of the internet. And so if you have enough hard drive space, you can go to this place, and you can download a copy of the internet from a certain date. And so we did that. We downloaded the last 3 copies of the internet. And then the students' project was to work out how to find and identify and download every single PDF on the internet. And we focused on .coms, .govs, URLs that kind of made sense for what we were looking for. And we've downloaded about 40 terabytes worth of PDFs. And we've crashed the university supercomputer several times. But it's all for a good cause. So once we have all this evidence in one place, we need to sort it out into what we're interested in. And so this, which is going to look tiny to you, is our evidence pipeline. So the first thing we need to do is kind of work out what it is that we want from that data. And for us in the Conservation Evidence Project, it's really easy because we have a 30,000-word document which tells us exactly the kind of studies that we're looking for. And so we compress this down into a kind of inclusion criteria that the model could check against to see if a paper meets these inclusion criteria. So we came up with our first version of this inclusion criteria, and then we went through an iterative process with a large language model. And what we did was we gave it our inclusion criteria, and we said, given this inclusion criteria, what papers do you think will be really hard to classify based on the criteria that we have? And it would then produce some synthetic, some fake examples of papers that it thought would be very hard to classify given our inclusion criteria. And then we could assess them as a team, we could think about it, we could say yes, no, and this is why, and we fed that back to the model to help us improve our inclusion criteria. And we did that for a couple of hours with the team, and then we came up with something that we felt was pretty solid. So once we have our pretty solid inclusion criteria, we want to be able to pass this on to the models. And so this is a completely plug-and-play system. It's not restricted to any type of model. We can switch the models in and out. It's completely self-hostable, so you don't have to send information through APIs to like OpenAI or Meta. It's all hosted within the university, which means that we can use documents that you might not want to leave your institution. And so the first thing we do is we have a very small language model. It's not a large language model. This is a very small one. And the reason we use a small language model is for efficiency and because it doesn't need to be very big. You don't need a sledgehammer to crack the nut. And so we have a small model which reads the titles and the abstracts of a paper against our inclusion criteria and decides whether it should be included or not. And then it produces a ranking for all the papers that we have. And once the high-ranking models then get passed to a large language model. In this case, it was DeepSeek R1 distilled into a meta model, so it was much smaller. But it was a very big model compressed into a smaller model, and that's where the papers got fed next. And they'd make the exact same judgment as the small language model. They'd say, given this inclusion criteria and the title and the abstract of this paper, would I include it? And if it would include it, it feeds that information back to the very small ranking model saying, well done, good job, keep going, this is the kind of thing we're looking for, building up that kind of archive of positive cases so it can help the ranking model do a better job. And we also asked the large language model to make the decision 5 times independently. And the reason for that is you kind of get a bit of a vote counting kind of system. And so some of the papers would just go straight through, 5 out of 5, we think this is great. Some of them would be more like 3 out of 5 times it would think it would pass. And we take that. We take anything that passed 3 out of 5 times, and then we pass it to our next model. And the next model doesn't just look at the title and abstract, but it looks at the full text of the paper. And we can do this because we've downloaded millions and millions of full-text papers. And so it's not just looking at the title and abstract, as you would in a normal kind of evidence synthesis situation. It looks at the full text of the paper. And if it passes that stage, it goes on to another model, which then extracts key pieces of information from that paper. But I thought it'd be vaguely interesting to have a closer look at the ranking model. I don't know how much people know about large language models. Some of you probably know loads, some of you probably not much at all. And if you know loads, I'm sorry. I'm not trying to teach you how to suck eggs. But the first thing I need to talk about is dimensionality reduction. So this is a 2D slice through a 3D space. And if you look at this, it's quite hard to work out what this is an image of on this graph right here. And we can move this image around, and we still get another 2D slice of this 3D object. It's still quite hard to tell. Could be some kind of dog. Another 2D slice. But this is the 2D orientation. This is the 2D orientation of a 3D shape that gives us the most information that allows us to understand that this is, in fact, an alpaca or a llama. I did say I was a biologist, but it's one of those. So this is the idea of being able to rotate these objects and be able to take a 2D slice that gives you the maximum amount of information. And this is the same for graphs. So this is like a 3D point cloud. You can draw a 2D plane through that, and then you can have a graph in 2D which gives the best kind of estimation of the kind of variance within that space. It gives you the best idea of what that 3D space looks like in a 2D graph. And in large language models, the space and the distance between points or between spaces within the large language model encode some kind of semantic meaning. And by semantic meaning, I mean the different kind of nuances that we have on certain words in certain contexts. So in the case of these words, we have king and queen, royal, masculine and feminine, gender terms, a noun, music, verbs, ran, walked, swam, but these can change, so you could have king goes with masculine, queen with feminine, past tense verbs. We could then, if the model has any understanding of the band Queen, it might put queen with music. And so this is all about how large language models can understand the relationships between different words. And when you look inside a large language model, so when large language model, frontier models say, oh, our large language model is completely open source, it's completely open, anyone can see it, this is the kind of thing that you see. You just see a long list of numbers, which doesn't mean anything to anybody. It only means something to the model. And what these numbers are essentially points on axes in this multi-dimensional space. So we all understand 2D graphs, probably, I hope. And so you can say that this dot is at 1.1 on the x-axis, 1.5 on the y-axis. You can add another dimension. You can be, oh, it's 0.4 on this next dimension. And then we can't imagine anything else because we can only see and imagine in 3D. 4D completely escapes us. When we're talking about billions of different axes, that's something completely different. And so basically all of these numbers indicate locations along lots of different axes within a multi-dimensional space. And so words are kind of plotted within this space. And if you take the distance and direction between different words, you'll then reach other words that have similar kind of semantic meaning. So if you take the distance between man and woman, and you find the word uncle, and travel in that direction and distance, you'll reach a word like aunt. Or from nephew, you'll reach a word like niece. Or father, you'll reach mother. So there's a direction in this space which is decided to encode some kind of gender information about words. And this is a 3D slice now through a multidimensional space. And the same applies to food. So if you take the distance between Japan and Germany, and then you travel that same distance from the word sushi, you might reach a word that's a bit like bratwurst. And so this is a demonstration of our ranking model. And so this is this massive dimensional space. And each dot in this space is a different paper. It's a different title and abstract that's been plotted within this space. And what the model is doing is it's trying to work out whether those papers are relevant or not. And they turn green when they are relevant, and they turn red when they're not. It looks like it's kind of on one side and working towards another, but if you could see all the dimensions, it would be working from the center towards the outside, and then it would get to a point where it's like, I'm not finding anything relevant anymore, so I'm just going to stop. And this visualization was built by a 14-year-old who we had for a summer work experience for a week. He built it in a few days. He then built it so it ran on all kinds of different platforms. The kid is insane. So quickly, I'm just going to end with an evaluation of our pipeline, just to kind of show how well it worked for us. So the one thing we have within the conservation evidence group is that we've done all this by hand for years. And so we have these kind of gold standards that we can compare our model to. So we said, how good do you think the model will be at recreating our butterfly and moth synopsis? And so what we did is we gave it the 150,000 papers that we'd looked through by hand several years ago when we did it. We gave it the exact same papers. We had our inclusion criteria, and we said, off you go. See if you can do it. So 150,000 papers went in, 1,439 papers came out, and then Will did some analysis, and we found out that it found all but 4 of the papers that we had included. And when we looked at the additional papers, so say there's about 400 papers, it found an extra 1,000. And we thought, they must all be false positives. So we started looking through those, and we actually found that about 25% of them were actually relevant, and we had missed them. And the reason that we'd missed them is because we don't read the full text of papers, and nobody does when they're doing evidence synthesis. And so there are all these little interesting bits of these interesting nuggets that are hidden within the full text that would be missed otherwise. And so it's taken 150,000 papers down to this very small square. The squares are to scale. Thank you very much. And we worked out that it would take about 1.5 years if you were reading a paper a minute for 6 hours a day and making accurate decisions all that time to get through 150,000 papers, which would cost us about £127,000 to do. But the AI, our first pass at this pipeline, did it in about a week. It took 2 weeks and cost us about £1,000. So there's a large applicability for this. And it's not just for conservation. We've designed this in a way that we could apply this to any question. So we're working with policymakers and decision makers to try and work out how we can use this to help inform decision making across all kinds of different things. And that's it. And here's some other papers that I've written on this subject. Thank you very much.